Okay, welcome back. We're today going to start the second major topic in Unit 1, which is Newton's laws. Newton's laws revisited in a way because Newton's laws of motion were covered in Physics 2204 as well, but there's a couple of new twists put on Newton's laws in this course, Physics 3204. But before we do go on, just a couple of quick reminders about the first major topic, or the first set of topics that we've covered, and that is projectile motion. Just a couple of real quick things that you need to keep in mind. Remember that, first of all, there are three different cases. There's the horizontal launch, when a projectile is launched horizontally, like rolling off the edge of a table or off the edge of a cliff or those types of things. The key to those questions is that the initial vertical velocity, v1y, is always zero, always, in the horizontal launch projectile motion problems. So keep that in mind. In the angled launches, which is case 2 and case 3, and we called case 2 the angled launch upwards, and we called the third case, case 3, the angled launch downwards. And whenever you have an angled launch, your initial velocity and an angle of launch, you always find the components, Vx and Vy, at the beginning. Now remember, the Vx doesn't change throughout the motion because that's constant. That's another very important thing to remember, that Vx is constant. And V1y, which is equal to V sine theta, will always be a positive number for the upwards launch, but it will be a negative number for the downwards launch. That's very, very important. That is the most common mistake with those types of questions, forgetting that negative sign for your downward initial velocity. Okay, that's very important because that's going to have a huge impact on the time that the object remains in the air. Okay, so try to remember those things. Remember, like I said, V1y is 0 when you have a horizontal launch. V1y equals V sine theta when you have an angled launch. Positive for the upwards, negative for the downwards. Okay, so try to keep that in mind. The Vx for the angled launch is going to be V cosine theta. And remember that it's constant for all parts of the motion, because it's uniform motion horizontally, because we ignore the effects of air resistance for those problems. So the only one you have to worry about for acceleration is the vertical, and remember that the vertical acceleration is always negative 9.80, always, for projectile motion problems. All right, so that's a quick summary of the projectile motion. The first 4 lessons, the first 4 topics, dealt with some kinematics review and the projectile motion cases, horizontal, angled up, and angled down. Okay, so that's topics 1 through 4. Today we're going to start topic 5, which gets us into the second part of Unit 1, and that's all about Newton's laws of motion. So what we're going to do first is we're going to do a real quick review of Newton's laws. And if you remember from Physics 2204, and in fact you probably did a recap in Physics 3204 with your teacher as well, there were 3 laws of motion proposed by Sir Isaac Newton. Okay, and he just called them the first, second, and third laws. That's it. Pretty simple. And let's just do a quick recap of those. So Newton's first law, also known as the law of inertia, because inertia, as you should remember, is the tendency of an object to resist changing its motion. So in other words, if it's not moving, it wants to stay that way. If it is moving, it wants to stay that way. Okay? It wants to stay that way. And a measure of an object's inertia is its mass. So the more mass an object has, the more inertia it has. Okay, and you might think, you know, it'd be nice to be up on the space shuttle or the International Space Station orbiting around the Earth, because it'd be so easy to move things around up there because they're weightless. But even though they're weightless, they still have inertia. So if someone were to throw a 50-pound cannonball at you in space, it would be just as hard to catch as that 50-pound cannonball being thrown towards you on the Earth. Okay, it wouldn't be a whole lot of difference, because it would still have that same inertia, because its mass would be the same whether it was in space or on the Earth's surface. So inertia is still in play. Okay? The inertia doesn't reduce when you go into space. Objects that are weightless still have inertia. Okay, so try to remember that. So just to summarize then, Newton's law has two parts. First of all, objects that are at rest tend to stay that way, and there's a catch, and the catch is unless they are acted upon by an external unbalanced force. The unbalanced part is very important, because if the force is not unbalanced means it doesn't cancel out. So you might have, for example, two forces. Like if you're sitting down now listening to this, you're exerting a force on the chair because gravity is pulling you down, but the chair is also pushing up on you. Those two forces are balanced. They cancel each other out. There's no unbalanced force acting on you. That's why you continue to stay there. You continue to sit there. But if someone were to come along and give you a big push to try to knock you off the chair, then chances are then you'd move. But anyway, objects at rest tend to stay at rest. The other part of it is objects that are already in motion also tend to stay that way. Okay, and you've all experienced this. That's why you wear a seatbelt in a car. Because if you're moving in the car and the car should suddenly stop because of an accident or because of trying to avoid an accident, then the seatbelt is what keeps you from continuing to move forward after the car has stopped. Because otherwise, if you didn't have the seatbelt on and there was no airbag in the car, you just keep on going till you hit the steering wheel or you hit the windshield or whatever, because objects in motion tend to stay in motion. It's also why it's not a good idea to lay a big heavy book like your physics book in the rear window of the car, because someone in the back seat, if the car were to suddenly stop, that book is going to keep on moving and it's going to slide right out of the back window and right up the back of someone's head. So inertia makes it very unwise to lay objects like that without having them fastened down. Okay, same thing, you may have seen this happen before. It actually happened to me one time. If you lay something in the back of a pickup truck and you start off too fast, okay, because that object has a tendency to stay at rest, it will want to stay at rest and it can slide right out of the back of your truck. Okay, so again, inertia at work. So that's Newton's first law. Now, we don't use that one a whole lot in Physics 3204, but it's worth mentioning because it's one of the three laws of motion. The second one, however, we use a lot. Okay, in especially when we start talking about inclines and things like that, Newton's second law, very important. So Newton's second law kind of builds on the first one, because the first one tells us what happens if there's no unbalanced force. Okay, if there's no unbalanced force, Newton's first law applies. In other words, objects at rest stay that way, objects that are moving stay that way. But what happens if there is an unbalanced force? That's where the second law comes in. The second law, Newton tries to explain exactly what will happen when there is an unbalanced force. Okay, so as long as the forces are balanced, there's no change in the object's motion, but, big but, if there is an unbalanced force, or a net force is another way to say that, it will cause the object to accelerate. Okay, and Newton went one step further as well. He said not only does it make it accelerate, but the acceleration is directly proportional to the net force acting on it. And what that means simply is this, that if we double the force, you will double the acceleration. If you triple the force, you will triple the acceleration. That's what directly proportional means. Whatever happens to one happens to the other. It's proportional. The net effect is the same for both. And the other way works too. If we half the force, you will half the acceleration. The other side of it is acceleration is inversely proportional to mass. Inversely proportional to mass. In fact, if you put those two things together, you would say this: acceleration is actually equal to force, because it's directly proportional to force, over the mass. The proportionality constant for this relationship is actually 1. So we don't need a proportionality constant, in other words. A equals F over M, which means F equals M times A. That is the equation form of Newton's second law. That's Newton's second law in equation form. So that one comes in very handy because it allows us to calculate, for example, the acceleration of an object if we know the force and the mass. And we're going to use that equation fairly extensively over the next little while, over the next 3 topics. Okay, and even a little bit in the topics after that as well, because forces play a major role in most of Unit 1. Most of Unit 1 in this course. So the equation form of Newton's second law is F net equals ma. And the reason we say F net is because the object only accelerates when there's an unbalanced force, when there's a net force, in other words. Alrighty. Let's move on to the third law then. Or actually, yeah, before we do, there are 2 ways to actually calculate net force. Okay, we just mentioned one of them. The net force is F net equals ma. That's one way to do it if you know the mass and the acceleration. But the other way to do it is we can sum the forces. That's what this little symbol here means. You may have come across it in math. It's the Greek letter sigma. Okay, and sigma means sum of. And sum of means you add things up, add them together. So F1 plus F2 plus F3, etc., 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 depending on how many forces there are, equals F net. Now, mathematically, you can only add forces that are either in the same direction or exactly opposite. So we'll talk more about that now in a few minutes. But because both of those things equal F net, we can actually combine them. Look right here. The sum of the forces, which is F1 plus F2 plus F3, etc., etc., if that equals F net, then it also equals M times A. And we are going to use that relationship extensively over the next few topics. Now, the most important one of all, though, and I want you to remember this because this comes up on almost every single public exam. You'll see those words at rest or constant speed. Remember, if it's constant speed or at rest, the acceleration is 0. And if the acceleration is 0, that means there's no net force. There's no unbalanced force. Okay, that's really important. And we're going to look at an example now in just a minute where that's the case. Let's take a look at the third law. The third law is also not used as much in Physics 3204, but again it's worth mentioning here, and I'll tell you why. The third law says for every action force there is an equal and opposite reaction force. So in other words, if object A exerts a force on object B, then that means that object B in return exerts the exact same magnitude of force but in the opposite direction on object A. Okay, so that's what we call an action-reaction pair. And that negative sign you see there, all that signifies, this one right here, that negative sign right there signifies that that is the opposite direction. Now, the most important thing of all to remember about action-reaction pairs is they do not cancel each other out. Even though they're in opposite directions but equal in magnitude, normally you'd think, well, they must cancel each other out. Well, if that was the case, nothing would ever move because every force has a reaction force. If they always canceled out, you wouldn't be able to drive your car down the road because it wouldn't move. So obviously, they don't cancel out. The reason they don't cancel out is because they act on different objects. They act on each other. One force acts on object A, the other force acts on object B. That's why they don't cancel out. Now, the reason Newton's third law of motion is so important is because it results, or it gives us, a force that we call the normal force. And the normal force is the force that is exerted on an object by the surface. A few minutes ago I just mentioned that when you're sitting on a chair, Okay, gravity is pulling you down. It's pulling you against a chair. So your body exerts a force on the chair. In return, the chair exerts an upwards force on your body. We call that the normal force. And it's actually a reaction to the force your body is exerting on the chair. It's a reaction force. Okay, but it's important that it be there, because if it wasn't, gravity would pull you down, and if there was nothing holding you up, you'd fall down to the floor. So that chair exerting a force on you is very important in that case. It balances out the force of gravity so you can not move, so you stay still. Okay, so that's Newton's third law. And like I said, most important because it gives us the concept of a normal force. And we're going to talk more about that one in just a minute as well. The final thing that we're going to get into before we actually look at a couple of examples are the whole concept of free body diagrams. Again, introduced in Physics 2204, but used extensively in Physics 3204 as well. And a free body diagram is sometimes called a free body force diagram, because what it is, it's a diagram that shows all of the forces acting on an object. Every force acting on an object all together. That's what we call a free body diagram. Now normally, the way free body diagrams are drawn is with all the forces pointing outwards from the object, and they're all acting from the center of mass of the object, the center of the object's mass. So take a look at this diagram here at the bottom. We got a diagram right here at the bottom of the screen, bottom left corner of your screen, that shows a number of forces acting on a sailboat. 4 forces acting on a sailboat. We got the wind, we got the buoyancy of the water pushing up on the boat, we got gravity pulling the boat down, and we got the drag or the friction between the boat and the water. Now, that is not a free body diagram the way it's drawn. Because, remember, free body diagrams, all forces point outwards from the object. So, let's draw the free body diagram then for that. Here's what the free body diagram would look like. Now, when I draw free body diagrams, I always tell my students to represent the object with a dot. You don't need to draw anything else. You don't need to draw a box. You don't need to draw the boat. You can if you want, but it's totally unnecessary. The dot is fine because that dot represents the center of mass, center of the object, which is where the forces originate. So let's draw the forces. Okay, if I do that, I get one force right here. There's F1. Okay, then I've got F2 pointing up, right there. Then I've got F3 pulling down, right there. And I've got F4 pushing back this way. So all of those forces are acting on the boat. Now I have a free body diagram because now all the objects are pointing away from the center of the object. Okay, and all the forces are shown. That's a free body diagram. Now I should label it. This is F1. The upwards force is F2. The downwards one is F3. And this one is F4. There's your free body diagram. Okay, and in this particular one, okay, the F1 and F4 look like they're about the same length, so they probably cancel each other out. F2 and F3 appear to be equal as well, so they cancel each other out. So that means there's probably no net force on that sailboat. Now, no net force on the sailboat doesn't mean the sailboat is not moving, though. All it means is if it is moving, it's moving at a constant velocity. In other words, it's not accelerating. That's all we know. Not accelerating. Is it moving? Maybe. But if it is moving, it's moving at a constant speed. Okay? In fact, I would say it probably is moving. If the wind is blowing on the boat, then there's a good chance that the boat is moving, isn't it? Okay? And the friction, the drag between the boat and the water, that doesn't really exist until the boat starts to move. Not much, anyway. Let's look at some examples. Some examples of how Newton's laws can be applied to fairly straightforward situations. So look at this one right here. Let me tell you the common mistake that people make with this. Here's the common mistake. a lot of people would say, well, the force of gravity, which is m times g, would be 15.0 times gravity, which is 9.80, and that equals 147 newtons. And people would say, well, in most of the time, you know, force of gravity is equal to the normal force, so the answer must be D. Wrong. It's not D. Because in this one, you'll notice, there's another force right here. Look, this applied force right here. So in the vertical direction, acting on this box, there are actually three forces. There's the force of gravity pulling down. There's the normal force pushing up. Now, if they were the only two forces, they would be equal. But in this case, they're not the only two forces. Just watch. We actually have the normal force pointing up, the force of gravity pointing down. Oop, hold on now. I can't say that, not just yet. I also have force Y pointing up. The Y component, in other words, of our applied force. Okay, you see it right here, look. That guy is pointing up too. That equals the force of gravity. And the reason for that is, the reason I know they're equal is because that box is resting on a horizontal surface. In other words, it's not moving up, it's not moving down. So if it's not moving up or down, that tells me there is no net force in the vertical plane. Okay, no net force vertically. So that means the force is upwards. Okay, the force is up. The sum of the forces up must equal the sum of the forces down. Okay, that I know that has to be true because there's no net force up or down. If there was, the box would move up or down, and it couldn't be resting on a surface then. So Fn plus Fy equals Fg. Now, if I want to figure out Fn, here's what I do. I bring the Fy over, and I subtract it. Anytime you've got another applied force, you need to do this. So essentially what I have now is I got my 147, but I have to take away that Y component of 4 newtons, 4.00. That equals 143, which is choice C. Okay, now that can be a little bit tricky, so be really careful with those. When you've got that extra force there, you need to worry about your net force being 0 up and down. That's pretty much always the case in this type of question. Okay, so it looks like that. Let's try another one that's very similar. Again, we're asked for the normal force. Okay, but this time it's a little bit trickier because it doesn't tell you what Fy is. So now the first thing I have to do is I have to find Fy. And remember, Fy, the Y component of a force, is just force times the sine of the angle. So 211 times the sine of 25.0, that will give us 89.2 newtons. That's my Fy. That's this force right here. Look, that's Fy. And you'll notice that because the force being applied is at an angle upwards, then the force Y is also upwards. Now I need to find Fg as well. And Fg is just mass times gravity. Again, 40.0 times 9.80. That equals 392 newtons. Now again, don't be tempted to take choice C. That's not the right answer. That's the force of gravity, not the normal force. Now sometimes the normal force is equal to the force of gravity, but not in this case because there's a third force acting vertically, that Fy. So I do the same thing. I know that Fn plus Fy, my two upward forces, must equal my downward force, which means Fn is going to be Fg minus Fy, which tells me it's 392, take away 89.2, which works out to be 303. The answer is actually B. So those types of questions, if you go back and look at all public exams, they show up fairly often. So brush up on that stuff. Okay, they do show up almost every year. Something similar to that. So like I said, know how to do those. Next question. If you read that question carefully, you will see a clue there. And the clue is right here. Constant speed. As soon as you see the words constant speed, that means acceleration is 0. Constant speed means there's no acceleration. And if there's no acceleration, that tells you there is no unbalanced force, no net force. So right away, the answer is A. Bingo. Quick as that. You know that's the answer right away. Because if there's a constant speed or it's not moving at all, okay, either or, constant speed or not moving, F net equals 0 every single time. That's the clue you look for. That comes up a nice bit on public exams as well, so be ready for that. Be ready for that too. Let's try this one. Free body diagram. Now it says, we got an inclined plane here, but I know we haven't talked about inclined planes yet, but I know you have done them in the course, but you don't even need to have done inclined planes to be able to answer this question. There are only 2 forces acting on this object. Force of gravity, which is always straight down. They all have that one. Force of gravity straight down. And the only other force is the normal force. And remember, normal force, because the word normal means perpendicular, the normal force is always perpendicular to the surface. So in other words, the normal force is going this way. That's Fn. That's Fg, straight down. So there's the one that represents that. The other one's got extra forces there that don't belong. They've all got extra forces there that don't belong. That's the only one that's right. And we'll look at one more example before we finish up this topic of review. And that is, in which of those free body diagrams would the net force not equal 0? Not equal 0. In other words, which one of those free body diagrams shows an object that does have a net force on it? Well, if we look at them in order, look at A, and you notice there's a force to the left, there's a force to the right. Okay, there they are, force to the left, force to the right. They cancel each other out. There's also a force down and a force up. They cancel each other out. So F net does equal 0 for that one. Same thing with B. Look, I got 2 forces up, so that's 2F. I've got 2 forces down, that's 2F. 2F up, 2F down, F net 0. But in C, 2F up, 1F down. So that means that the net force on this guy would be F, 1F upwards. So that's the one where F net is not 0. And D would be the same thing. The 2F, 2F, they're exactly opposing each other, exactly opposite directions. They cancel. The F to the left and the F to the right, they cancel. F net is 0 for D. That's what it looks like. So that concludes our quick review of Newton's laws of motion. And even though Newton's laws of motion aren't specifically introduced in Physics 3204, there are still questions there that relate to that on the public exam, because you have to know this stuff in order to be able to do the inclined planes anyway. Okay, so be ready for those types of things. Free body diagrams, important. F net, important. The fact that at a constant speed or stopped, F net is 0, important. Okay, so remember those types of things. Finding the normal force when there's more than 2 forces acting vertically, that's important. Like I said, that's there a good number of times on the old publics. If you go back and look at them, I guarantee you'll find it on almost every single exam. So if I were going to bet, it'd be a pretty safe bet that that's something you should know. So we're going to stop right there. Our next topic is we're going to take a look at some more Newton's law stuff, but this time we're going to do some with friction. We're still going to leave the inclined planes out for now, but we may do some with pulleys, and we're definitely going to do some with friction. We're going to see how friction changes it, because everything we've done here so far, there hasn't really been any mention of friction just yet. So we'll stop right there. Again, good luck with your studies. Good luck with your exam. And we'll be back with the other one as well.